So oftentimes people assert that rocket propulsion in outer space is not possible because there is no atmosphere for the thrust to push against. But actually, that is not true because rocket propulsion is a function of the conservation of momentum. So a rocket moving through outer space is essentially moving through a superfluid for which its inertia is held constant other than some solar winds. And so momentum is defined as the mass of a moving object times its velocity. So if we apply or improve on momentum by equating the momentum of the jet propulsion mass and velocity to the velocity of the rocket times its mass, we then have identified the conservation of momentum, which states that momentum energy cannot be created or destroyed, but only changed in form or transferred. So to improve on this, let's say we have 700 kilograms per second of gas flow discharging out of the jet nozzle of this rocket, and that is from the combustion of kerosene combined with 100% liquid oxygen. So we would have to have our own onboard oxygen source to support combustion in outer space. However, if we're in the atmosphere and we're using, let's say, gas turbines or even the same mixture of pure oxygen and kerosene, we would also have 21% oxygen in the atmosphere, unlike in outer space. So mathematically describing the conservation of momentum is by equating the momentum of the rocket with the momentum of the gas propulsion. So that is m1 times v1 is equal to m2 times v2. So let's say we had all the information except for the velocity of the rocket. We're able to algebraically solve for what the velocity of the rocket would be based on multiplying the mass flow of the jet propulsion times its jet velocity, then divided into the mass of the rocket. So upon doing so, we calculate a relatively slow 26.7 meters per second rocket velocity through space. So we'll just assume it's moving really slow around some sort of a reconnaissance satellite, and that thrust output is by design. So the velocity of the rocket without atmosphere includes the self-contained oxygen source. So that is the liquid oxygen reacting with the kerosene to support outer space combustion. So if we were to figure out what kind of thrust is occurring in outer space based on this scenario, we could just take the 700 kilograms and multiply it times the 457.3 meters per second final velocity. So that's about 1,500 feet per second. And then simply take that value, 320,110 newtons force, and divide it into 4.45. So we have approximately 71,935 pounds thrust. All right, now we got to compare the rocket traveling through Earth's atmosphere or through the air. So if the rocket is moving through the atmosphere or the air on Earth, then we have to also include the cross-sectional area of the jet nozzle, in this case square inches, then multiply times the absolute pressure of the jet propulsion itself as a function of absolute pressure. So that's the gauge pressure of the gas discharge pressure and the atmospheric pressure combined. So this will then result in additional thrust greater than what the thrust would be in outer space. So we'll just make up a scenario. Assume that there is 10 psi gauge pressure of thrust gas pressure exiting the exhaust nozzle, and then the rocket is just taken off out from Earth's sea level elevation. So we'll say just a little bit less than 14.7 psi atmospheric pressure. So let's say 14 psi atmospheric pressure added to 10 psi gauge pressure as the propulsion gauge pressure out of the nozzle. So 24 psi A absolute, and then 18-inch nozzle diameter. We can divide the 18 into 2 to get 9 inches radius squared, then times pi. So that is the cross-sectional area in square inches of the jet nozzle. Then multiply times 24 pounds per square inch absolute pressure. So we get an additional 6,107 pounds of thrust if it was the thrust pushing against the atmosphere. But most of the thrust, whether on Earth or in the atmosphere or in outer space, is a function of the conservation of momentum, which is an improvement of Newton's second law of motion, forces mass times acceleration. But we're equating two different masses and two different velocities because something's got to give. We can't create or destroy the momentum, so we end up getting the 26.7 meters per second rocket velocity as the vehicle itself, based on knowing the mass flow of the propulsion times its final velocity, and then the mass of the rocket itself. So again, we'll just assume this is some reconnaissance rocket going around a satellite, super slow, 88 feet per second, so about 60 miles per hour, but we're just proving a point here that outer space rocket propulsion is a function of the conservation of momentum. So if we want to get the thrust of the rocket if it was moving through the atmosphere, we could just take the 700 kilograms times 2.2, because we have to convert that to pounds, and then multiply it times 1,500 feet per second jet velocity, then divide it into gravity, 32.2, and we'll calculate 71,739 pounds force. Then we can add it to the pressure thrust of 6,107 pounds force. So we get about 77,846 pounds of thrust. So this is about 8% more thrust in the atmosphere. So that's about how much more thrust you're going to get if the thrust is pushing on the atmosphere. But if we completely remove the atmosphere, we went to a vacuum, or we went to outer space or some sort of outer space superfluid, and we carried our own onboard oxygen and used that to support hydrogen or kerosene combustion, we would still get the thrust, not because the thrust is necessarily pushing against the atmosphere, but because we are conserving the momentum of the jet propulsion with respect to the vehicle or rocket's momentum. So m1 times v1 is equal to m2 times v2. So if you ever get in an argument and someone says that rockets can't actually fly through space because there's no atmosphere for the thrust to push against, you can bring up the conservation of momentum and just say that it's m1 times v1 is equal to m2 times v2. And if they don't know what you're talking about, you can just explain the algebraic relationship which supports the conservation of momentum. Thank you for watching this video, and have a great day.